All right, geometry students, we are going to be doing lesson 2.5. So I am on page 56 of your student journals. If you would please turn to that page. Okay, so we talked about algebraic proofs, right? So we kind of know sort of the details of a proof. Now let's get into geometric proofs. So first of all, a proof. I'm not going to necessarily define all these 100%, but basically a proof is a logical argument that uses deductive reasoning to show that a statement is true. So think of a proof as kind of like, well, proof that something actually works, right? So it's like your guarantee. Like, this is why I know this to be true, right? And so there's like a detailed plan and there's justifications and so forth and so on. And so we can write proofs in a variety of ways. Actually, for, excuse me, for this class, we are going to focus on only a two-column proof. So there are other proofs where you can do a paragraph form in like a flow chart form, and those are fine. And if you like that type of format, they are in the book, and you're more than welcome to look through them. I am going to go through the two-column proof, number one, because it's the most common, and two, you're going to see it. So that all of us teachers here in Bloomfield Hills, we use it. And so when you are, seeing in other textbooks and, next year and the years after, when you're in math class, that's the kind of stuff that maybe they would reference, okay? So I'll show you what a two-column proof is, and it's easier to explain with a picture. And then last, not least, is a theorem. So theorems are going to be what we talk about next, which are basically rules that we know to be true in geometry. So let's talk about that, I guess. Let's start with the theorems, right? So we have a few different theorems. And so theorem 2.1. And again, I'm not going to make you memorize these theorems so much as to understand what they're actually saying to us. And so theorem 2.1 is talking about the reflexive, symmetric, and transitive properties. Those should sound familiar. We talked about them in the last video. And so now we're specifically talking about them for a segment. So for example, for any segment AB is congruent to itself. So I want to give you an example of where you might see this. So imagine you have a square. All right. And let's call this A, B, and then let's call it C and D. And let's say I drew a line from A to B. So if I was talking about this triangle here, and then I was talking about this bottom triangle, do you see how they both have line segment AB in them? So technically you could say line segment AB in the one triangle is congruent to the line segment AB in the other triangle. And we know that because it's the same exact line. We call that the reflexive property. So in other words, like in this case, like two triangles are sharing a common side. So that symmetric property, again, I don't want you to get that confused with reflexive. So the symmetric property is where they, like if two things are equal to the same thing. So if AB is congruent to CD, then you can say it the other way around. CD is congruent to AB. That comes in handy in those algebra proofs where we had like 5 equals X, but we wanted it to say X equals 5. So we just flip it. Transitive properties where if two things are equal to the same thing or congruent to the same thing, then they're congruent to each other. So imagine you have CD. So notice that you have both CDs here. So if AB is congruent to CD and EF is congruent to CD, then that means that AB and EF have to be congruent to each other. Again, we talked about that in the last video. That's what we're going to use when we do some of our geometric proofs here coming up. So this is for segments, and then for, they have a whole other theorem that's just for angles, but it's the same thing. So this is like reflexive angle. And so symmetric, we're talking about angles, and transitive talking about angles. Again, same exact thing. Reflexive still means something is equal to itself. Symmetric just means it's the other way around. We can flip it. And transitive means two values are equal to the same value, then they must be equal to each other. So it's easier, like I said, to kind of get into the proofs. Let's go ahead and look at what we're going to be doing today. So this is a nice little diagram of what a two-column proof is going to look like. So it says, in a proof, you make one at a time until you reach a conclusion. So remember in those algebraic proofs we did, okay, what did we do first? Oh, we added 2x to both sides. So then what did we do? We simplified. So again, it's very detailed and it's step by step by step. It says, because you make statements based on facts, you are using deductive reasoning. Usually the first statement and reason pair you write is the given information. We did that algebra proof. Remember, we started with an equation. We called that our given. So when we talk about a geometric proof, what you're going to notice is that you're going to be given or provided a given. In other words, this is your starting point. So I always like to kind of think of this as where I start. So this is kind of like where I start my proof. And then the proof, okay, that's the end of my proof. So this is where I'm starting, and this is where I need to end. So everyone's proof should be the same start and the same end. Not everyone's proof will be exactly the same. I mean, they will be very similar, but you could have it in a little bit different order and still be correct. But the start and end will always be the same. So if you notice, they're given, it says copy or draw diagrams and labels given information. Do not mark or label the information in the proof statement on the diagram. So what you're looking for is you're given kind of like a diagram here about two angles. And so these are our statements. We call this a two-column proof for obvious reasons. There's two columns. One side is called statements, one side is called reasons. So you will need to, when you draw your proofs, you will be kind of drawing this T-chart. We always call it a T-graph. And on one side you'll write the word statements, and the other side you'll write the word reasons. And then as you're kind of going through, these are going to be my statements, things I know to be true, and this is the rationale as to why. So this is where you're going to write like symmetric property, definition of congruence, or whatever reasoning you know to be true. So let's do one together. So this is actually kind of partly done for us, which is nice, and we're going to kind of work our way up, and then eventually we'll get to the point where we're going to write our own proofs all together. So notice the given. It says given A, B, and C, D bisect each other at point M, and line segment BM is congruent to line segment CM. So what if you noticed here, I started my proof with part of my given. So line segment BM is congruent to line segment CM. When I know something is true, I mark it on my diagram. So B to M is congruent to C to M. So what I'm going to do is I'm going to mark on my little diagram here that those two pieces are congruent. All right, so let's follow along what they did here. So CM is congruent to D to M. All right, so we used this part of the given. If anyone provides you with a given, you have to use everything in it. There's a reason why we say it in the proof. So this part, A, B, and C, D bisect each other. So we're going to use a lot of those definitions that we spent the first, all of September, right, learning. So we're going to use definitions about bisect. So if A, B, and C, D bisect each other, it means those two line segments, all these pieces are going to be equal. So A is bisected, which means that, and this side is bisected. So if these two pieces are equal, and then if this piece is labeled 1 and it has to equal this one, then this has to be labeled as 1 dash. Likewise, so does this. So CM is congruent to DM. Why do I know that to be true? Well, I know that to be true because in the given it said that it was being bisected. So we call that definition of bisects. So I'll give you a little hint. Anytime we use a word like bisects, is a midpoint, anything like that has like a specific name, one of your reasons will be definition of that term. So like I use bisects in here, so I'm going to talk about definition of bisect. Next, we said BM and DM are congruent. So pay attention to what we have up here. I have BM is congruent to CM. CM is congruent to DM. How do I know that BM is congruent to DM? Well, that's transitive property. So remember when two things, so line segment C to M, are congruent to the same thing, that means they have to be congruent to each other. So this is how you will see transitive property. So basically what we're using is we're saying, okay, we got the first two statements from the given. Well, what does that given help me determine next? And so that was that transitive property. The given helped me be able to use the transitive property. So now notice the difference between statement 3 and statement 4. We went from line segment BM is congruent to line segment DM to B to M is equal to DM. So we went from congruent to equals. Why do we know that to be true? Well, if we remember our conversations, several videos ago, we talked about how we know that if two things are congruent, then we know that their lengths are equal. So again, we went from congruent to equal. This would be because we know the definition of congruence. And I'm a big fan of using symbols instead of words, so if you don't like to, by all means, go ahead and write out the word. So I know those two things are equal. So B to M and D to M are equal. All right, look at our reasoning for this one, segment addition postulate. So the segment addition postulate says that basically if you add these two segments together, it equals the whole thing. So if I know, my goal is to get AM equals AM plus, A to B equals AM plus DM. I want to say something about line segment or the distance of A to B. So I'm going to use that segment addition postulate. So from A to B, that is the same thing as me saying A to M plus B to M. And you might be asking yourself, well, how would I know that just from looking at it? And so again, part of it is you know where you want to end. You know that this is your ending point. So you know you have to kind of somehow get A, B as part of your statements in order to end there. Obviously, I gave you parts of the stuff already included. So, we could kind of work backwards and look at that. But you also have to kind of think about where your proof is heading. Like at the end here, we know we need to have AB equals AM plus DM. All right, so what's this last statement? So the only difference here is I swapped out B to M and D to M. How do I know that to be true? Well, if B to M is equal to D to M, then that's what we call that substitution property. So all I know is since these two things are equal, BM and DM, that means wherever I see BM, I can replace it with DM. And that's what I did. So this is your first geometric proof. The nice thing about proofs, and yes, I said there are some nice things about proofs, is that there's a lot of structure, right? So they're always kind of done the same way. And so eventually, the more we do, the easier it becomes. With that being said, let's do some more. Now we're on page 58. So again, this is another fill in the blank type proof. We do a lot of these, especially at the beginning as you're learning. So pay attention to your given and pay attention to your proof. This is where you start, this is where you end. So AEB is a complement of BEC. AEB is a complement of BEC. Okay, great. So again, think of the word complement. If I give you a definition, notice I'm going to use that definition in my proof. So what does the definition of complementary angles tell us? Well, if ABE and BEC are complementary, that means they form a right angle. That means if I put them together, they equal 90 degrees. So the measure of angle AEB plus the measure of angle BEC equals 90 degrees. So lots of things I'm going to be looking for here when you're doing this correctly. You got to have that little M there because that means measure. So measure of this angle. It's not, whenever you're talking about a number, it equals 90, you should use the little measure. So measure of angle AEB, make sure you have the angle symbol, adding to the measure of angle BEC equals 90 degrees. All right. Now we say the measure of angle AEC is equal to the measure of angle AEB plus BEC. This, basically what they're saying here is AEC, this big angle, is equal to this plus this. Well, that's called angle addition postulate. Remember how we did the segment addition postulate? Whoops. Angle addition postulate. So the angle addition postulate basically says, these two angles added together equal the whole angle. All right, AEC equals 90. AEC equals 90. Well, how do I know AEC equals 90? Well, if you look at your drawing, I guess, we could do a couple things. What I noticed here is since AEB, measure of angle AEB and the measure of angle BEC, this equals 90. This is called our transitive property, right? If the measure of angle AEB plus the measure of angle BEC equals 90, and the measure of angle AEB plus the measure of angle BEC equals the measure of AEC, then those two things have to be equal to each other. It's a lot to say. But again, do you see it? Do you see that transitive property there? So they both had like these two things in common, so those two things have to be equal to each other. All right, AED, that's this angle over here, plus AEC equals 180 degrees. Definition of supplementary angles. Okay, so that one worked. That one's already provided for us. And then the next statement, we're going to say they are using the substitution property. So what are they substituting in? What do you want to guess? Well, a lot of times what you look for is you look what came right before it. So if we look at the previous two statements, we know AEC is 90, but then we have AEC here. So what I can do is I can substitute AED. I can say I'm going to substitute in 90 for this. And that would be the substitution property. So all I did is just took this, because I knew this issue, and just substituted in there. And then how do I know that AED equals 90? Well, what did I do to get from here to here? Looks like all I did was subtract 90 from both sides. So we call that the subtraction property of equality. All right, there's your proof. Let's keep going. So on this one, number 3 says it's not really having your proof, it just says name the property. So if RST is congruent to TSU, these are angles, and TSU is congruent to VWX, so again, they have this in common, then what do we know about these two angles? Well, that's a classic example of the transitive property. All right, so this one, segment GH is congruent to JK, and then what about the other way around? JK is congruent to GH. That is your symmetric property. So just kind of reiterating those two properties and how they would show up. All right, let's do our own proof. One full proof from start to finish. All right, so I'm not making you draw the little T-chart here, but that's how you would do it. Put the statements and reasons. You're given a diagram, you're given the given, and you're given the proof. So what I want everyone to start with is your given. So you write it down exactly the way it's written. M is the midpoint. I'm going to use MP for midpoint of line segment RT, and you're going to do given. Notice what I'm doing here. The statement number 1 and reason number 1, they have to match. It should be in order. Like if you notice up here, it's all nice and pretty in order. It goes right across. Like it shouldn't be all like mismatched, okay? I know that sounds stupid, but it can help. All right, that's all we're given. What do we do next? Well, if M is the midpoint of RT, so what do we know about a midpoint? If M is the midpoint of R to T, so then what do we know about R to M and T to M? Well, if M is the midpoint, then those two pieces have to be equal, or in other words, congruent. So I'm going to say RM is congruent to TM. How do I know that? Why do I know those two pieces were congruent? What? We use the word midpoint in our given. You have to use the word definition of midpoint as one of your reasons. All right, notice where we're headed here. We're not talking about congruency. Our proof has all about equality. So let's change our statement here. So we already know if two things are congruent, then they have to be equal. And we did that in another proof. So what you're going to notice in a lot of these proofs, we reuse some of the same statements and reasons that we've done in other proofs. So from congruence to equality, remember we talked about that. This was definition of congruent. So by definition of congruent, we know that the distance from R to M and the distance from T to M are equal. Okay. We need to be able to get to something like this. M to T is equal to RS plus SM. So we need to do something about like making an equation, like with a couple things. So that's called this segment addition postulate. Anytime you're trying to, basically add two things together to equal a third thing, it's going to be a segment addition postulate, or if it was angles, it'd be angle addition postulate. So what we're going to get at is I'm going to talk about, since I want to do something with RS and SM. RS and SM are right here, okay? What do I know if I put those two things together? Well, I know I have to show that it equals MT, but right now if I put RS and SM together, it should equal RM. So I'm going to say R to M equals RS plus SM. And the reason why is that segment addition postulate. So again, I'm trying to think about where I'm trying to end and what am I providing? What can I use to kind of help me? So I noticed that if I put those two pieces together, it equals the whole thing. All right, statement number 5. Do I have enough to end this? So like all I really need to do, I've got RS and the SM. I need to change out the RM with TM or MT. So how about we do it that way? How about we say, okay, since RM is equal to TM, we can say these two things are equal. What did I just do here? If I know that RM is equal to TM, then I just substituted TM or MT in for RM. So that was our substitution property. And now, since I'm already down to the given, I know I'm done. This is my end. So I had 5 statements, 5 reasons. Notice how they all lined up nice and pretty. Everything was kind of, as is. That's what I would like you guys to do. It is going to take you a minute to be able to do these proofs. It is always going to be easier the more proofs you do. Okay, so I would practice, practice, practice. So go on to big ideas, practice this lesson. We're going to be doing a lot of practice in class, but still you need to kind of do some extra practice just to make sure you're on the right track. If you have any questions, bring class, and I'll see you next time.